Bernoulli. Okay, so we're looking at a Bernoulli example here. What we have here is a tube with a wide opening over here on the left side and a narrow opening here on the right side. And we know that some water is flowing through this perfectly horizontal configuration. There's no change in height here, such that this is some V1, and then out here, this is some V2. And V1 is 2.95 meters per second, and V2 is 5.35 meters per second over here. We know what the gauge pressure of P2 is. We know that this is equal to 7.36 times 10 to the minus 4th pascals. What we're looking for in this problem is what is the gauge pressure at P1? Now, before we actually start diving into this, what do you think is going to happen to the gauge pressure here? Is it going to increase, decrease, or stay the same? Pause the video, put your guess on a piece of paper, and then unpause it and find out. So we took some guesses, talked about a few things. One of the Rosses named Thomas, arguably an average Ross if there ever was one. Or one of the best, who knows? We still have to see. He made the argument that this pressure here, P1, will actually be greater than P2. And the argument he made was that P1 plus rho G V1 plus, or excuse me, that's incorrect. That's yeah, rho G Y1 plus 1/2 rho V1 squared has to equal some constant, right, of the things on the other side. On the other side, if the velocity went up, then that means that, between the heights didn't do anything over here. So that means that our pressure on this side would have to go down. So we know that P1 has to be greater than P2. If we actually did want to solve this, we could say P1 equals P2 plus 1/2 rho V2 squared minus, and then bringing the 1/2 rho V1 squared to the other side, 1/2 rho V1 squared. And that will give us our answer for P1. In this problem, our water, or our fluid is water, so we know the density of water. We can just say that is 1,000 kilograms per meter cubed, or 1 gram per centimeter cubed. However you want to think about that. I guess we're in meters per second, so we might as well use the meters here. And we know our pressure here, so we've got 7.36 times 10 to the minus 4 plus 1/2 times 1,000 for the density of water, multiplied by V2, which was 5.35 squared minus 1/2 density of water is 1,000 times the velocity of V1, which was 2.95 squared. All of this will equal P1. And now, this is an exercise for the calculator, which I'm going to be very honest with all of you out there, I don't really want to do because I hate numbers, but we're going to do it anyways. I like to start with all the squares because I hate them. They're a lot of decimals and they get everywhere. 5.35 squared times 1,000 divided by 2. That means this is going to give us 14,311. And then 2.95 squared times 1,000 divided by 2 is going to give us 4,351. And this is 7.36 times 10 to the minus 4.
Isn't it to the positive 4?
Is that to the positive 4? Did I miswrite that?
Our paper states positive.
Nope, it's a positive. I'm a scrub. That should be positive right there. Because looking at these numbers, that didn't make any sense for that to be a negative. That is such a small number in comparison. That's definitely a positive. If you had negative 4 pascals, you're like nearly in a vacuum. And we knew that P1 had to increase, so here we go here. So let's see, we've got 7.31 times 10 to the 4th plus 14,311 minus 4,351 gives us a final value for P1 of equal to 8.3 times 10 to the positive 4th newtons per meter. And just like Mr. Ross told us, this pressure did need to increase. Faster moving fluids will have lower pressures. Slower moving fluids will have higher pressures. So it allows planes to float on the air, or rather be lifted by the air. But this problem is finished. Adios, take it easy.